There are two types of electrons for a specific atom. The electrons occupy the orbitals in the outermost shell with the highest n value are called valence electrons. And the electrons occupy the inner shell electrons are called core electrons. So, for example, if we look at the sodium, sodium has 11 electrons since it's number 11 in the periodic table. And the electron configuration is 1s2, 2s2, 2p6, 3s1. So the one electron in the 3s orbital, which has the highest energy level N3, that's the valence electrons. And those electrons in the inner shell orbitals are called core electrons. So often we can use a noble gas configuration to basically shorten the way we write electron configuration. So basically, we use the electron configuration. We use a noble gas, the symbol in brackets to represent the electron configuration of the previous noble gas before the element. So for sodium, the element, the noble gas before sodium is neon. And neon has 10 electrons. So we represent those 10 electrons using neon in brackets and plus the valence electron 3s1. So that will show us the noble gas configuration, which also shows us the valence electrons. In this case, sodium has one valence electrons. Now, similarly, if we look at the selenium, has 34 electrons. If you write the full electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p4. All right, so make sure you keep in mind that 4s is written before 3d since it's lower in energy based on the off-Bohr principle. All right, now the noble gas before selenium is argon, which has 18 electrons. So we would represent this 18 electrons using argon in brackets and write the leftover electrons. So that's 4s2, 3d10, 4p4. Now you can see here the valence electrons are the ones in with the highest n number, which is a 4s2, 4d4. So selenium is in group 4a, it has 6 valence electrons. So now noble gas configuration can basically shorten the way we write electron configuration. It can also indicate the number of valence electrons. So now if we look at the potassium, potassium has the electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And if we represent using noble gas configuration, the noble gas before potassium is argon, and then right with the leftover 4s1. So that's your noble gas configuration. And based on that, we can easily identify potassium has one valence electrons and sodium has one valence electrons as well, since they are both in 1A. And silicon has the noble gas configuration of neon 3s2, 3p2. Now it shows you that silicon has 4 valence electrons, which is consistent with the fact that silicon is in group 4A. So now a pattern exists in the periodic table. We can categorize those elements based on what type of valence electrons they have. So for example, in group 1 and group 2, 1A and 2A, they only has valence electrons in a s orbital. So for example, if we write the valence electron for all of the group 1A, it's 1s1, 2s1, 3s1, 4s1. And for the group 2A, it's 2s2, 3s2, 4s2. So this is what we call S block. Now the sixth group on the right side from group 3A, 4A, 5A, 6A, 7, and 8A, and so helium is one of the exception. Helium only has 2 electrons, so it's a 1s2. It has basically it's a s block elements, but the other ones they are the p block. And the ones in the middle that are transition metals, they all involve d electrons in the valence electrons in the d subshell. So it's what we call d block. And the lanthanides and actinides, they are the inner transition metals. So they are all F block, since in the valence electrons, they all have electrons in the F orbital. So you should be able to roughly identify what element is in which block just by looking at their location in the periodic table. So generally, when we write the electron configuration of different elements, we follow the Aufbauer principle, right? So start with 1s, 2s, 2p, and 3s, and 3p, and 4s, and 3d, and 4p, and so on and so forth. But there are several exceptions. Those exceptions are identified experimentally. So, for example, copper, if we base on the Aufbauer principle, if you write the electron configuration, it should be argon 4s2 3d5, and chromium would be argon 4s2 3d4. But as a matter of fact, experimentally, it was determined that copper has the electron configuration of argon 4s1 3d10, and chromium has the electron configuration of argon 4s1 3d5. So this is because there is a stability associated with a half-filled or full-filled d subshell. If you remember, a d subshell has 8 valence, 8 as 5 orbitals, right? So if we write the valence electron, the electron configuration of copper, it's a 4s2, 2 electrons right there, and 3d9. Okay. So now this is expected based on the Aufbauer principle, but experimentally it was measured that one of the electrons from 4s orbital jumped to 3d orbital to fill the get a full filled d subshell. So you have 4s1 and 3d10, and this is more stable than 4s2 3d9. And so this is why when electron has been borrowed from 4s jump to 3d to get lower energy. And copper and chromium are the two exceptions you should know that follow the half-fill or full-fill d subshell, which is they are exceptions of the Aufbauer principles.